Today, in our second part of our molecular geometry discussion, we're going to look at the geometry of atoms that are attached around a central atom and what those possible geometries could look at. Let's look over here on this third page, and you can see a list here of the different structural geometries or electron pair geometries that there can be. There's only 5 of them. 5 different types of geometries: linear, trigonal, planar, tetrahedral, trigonal bipyramidal, and octahedral. And these shapes are formed depending on the number of electron pairs around the central atom. So we have a possibility of 2, 3, 4, 5, or 6, and those correspond to these different geometries. So let's look at these examples down here now. Normally I represent these with marshmallows, but we're going to attempt to look at these as kind of balloons on this two-dimensional surface and see if we can translate it to this. For the first one, this is our linear structure. Our linear structure consists of a central atom, and it's going to be attached to 2 peripheral atoms. And when it does that, keep in mind that the electrons that are being shared here between these 2 atoms, those are very repulsive and they don't want to be close to each other, so they're going to spread out as far as they can. And for 2 atoms attached to a central atom, 180 degrees is as far apart as it can get. Now the next one is our trigonal planar structure. The trigonal planar structure as an example is a central atom, and this time it's attached to 3 different peripheral atoms. Now those 3 different peripheral atoms are all on the plane with the board. In other words, you could lay this in your palm of your hand and it would lay flat. Those atoms getting as far apart as they can from each other is going to end up giving this like 120 degree bond angle between these atoms. And again, spreading it as far as possible, it's going to give this triangle shape. The next one is tetrahedral. Tetrahedral molecular geometries are formed when we have a central atom, and then we have 4 different atoms. And again, it could possibly be a lone pair of electrons that are out there. Now, this is the weakest of the shapes, I feel like. I feel like it should have, those bottom 3 should kind of be pushed up a little bit. But you can still see what's going on here. You have a central one here sticking up, straight up in the plane of the board. You have the 3 down at the bottom here in a tripod shape. They should all be equidistant from each other. All of these are like 109.5 degree bond angles here. No matter how you turn this molecule, it's going to look the same. Our next structure is our Trigonal Bi-Pyramidal. The Trigonal Bi-Pyramidal structure is going to have, I think of it as a hopping robot. And maybe you'll see why in just a moment. You have the central atom, and there are 5 different things attached to the central atom. Could be another atom, could be a lone pair. So you've got one up here. I think of this as being the head, and I'll put little eyes on. Whoa, his eyes are awfully sideways. Let's do better eyes than that. I can do better than that. So here's his little eyes, and he's hopping around on his little pogo stick. And when he is reaching out towards you to give you a hug, and behind him is his tail. So if you can imagine it like that, that's your trigonal bipyramidal structure. It's called a bipyramidal structure because if you attach all these lines, I think if you can think of this in 3D, you'll see that this ends up forming a pyramid on top. It also forms a upside down pyramid on bottom, hence the bipyramidal structure name. So each of these has these positions around the middle are different from the top and bottom positions. These ones around the middle that are perpendicular to the other 2, these are called the equatorial positions. The equatorial positions are the ones, again, around the center. Then the top and bottom ones, these top and bottom ones are called the axial positions. Those terms will be important here in a little bit. Finally, the bottom structure is our octahedral structure. The octahedral structure has a central element here, and then it's going to have 6 things attached to it. Could be atoms, could be lone pairs, but there's going to be one on the bottom, one on the top, and this time there are 4 floating around the center. They're perpendicular to the other 2. Maybe you could think of hugging arms out here, maybe with 2 tails behind. Be kind of a strange creature, but kind of looks like one of those old toys like jacks that we used to play with when we were kids. But anyway, that is an octahedral position, or octahedral structure. These are just some other examples, another type of drawing to help you visualize. You have these in your notes to help you visualize what some of these structures are that we're going to draw. There are several structures that we have to work our way through. The first thing that I want you to do is to look at these drawings, and you're going to want to draw these structures into your blocks on your notes first. So pause this so that you can draw the structures into your notes and have that part already done. We've already learned how to do this particular portion. If you don't remember how to draw the molecular structures, then you'll need to go back to notes 9-4, that video, and review that. So hopefully you paused and got that done. And now we're going to look at, once we have drawn these Lewis dot structures, we're going to look at how we tell what the electron pair geometry, the molecular geometry, etc., and whether this molecule is polar or not. Now, one thing we're not going to have to do this year, and you may have noticed it in the previous table, there was a hybridization column, but the AP people have decided that we're not going to really enter into discussions of hybridization at this point. So you're going to be able to mark this section out of your table. I didn't take it out completely because you know, who knows, at some point they may return to that discussion, but go ahead and mark that out of your notes. You do not have to do these drawings. I'll have another video made that will show you the extra credit on how to draw these structures. At the pre-AP level, you don't have to draw them. At the AP level, you're going to have to. So for the first one, all we're going to do whenever we figure out what kind of structure these have is to label this, or excuse me, is to count the number of pairs of electrons around the central atom. Here's a pair of electrons, here's a pair of electrons. So there are 2 pairs of electrons around the central atom. If you return back to a couple of pages previously, you'll see that 2 pairs of electrons, excuse me, around the central atom is going to give you a linear structure. And I'm not going to flip back and forth to that table. You can flip back and forth to it and look at what's going on there. But from now on, we'll just be writing these down without flipping back to the table. This is going to be a linear electron pair geometry. Since both of these are attached to atoms, then it's going to look exactly like it appears here. If there were lone pairs, we try to imagine not being able to see the lone pairs, and we get our structure from that. But neither of these are lone pairs, they're both atoms. So if there are no lone pairs on the center atom, the molecular geometry is going to be the same as the electron pair geometry. And we'll come back to the polar versus nonpolar in just a moment. On the next one, if you'll notice, and again, the first thing we do is count up pairs of electrons around the central atom. So each of the dashes is a pair of electrons. So there are 3 pairs of electrons around the central atom. If you turn back to your table, you will see that 3 pairs of electrons tells you that this is going to be trigonal planar. Trigonal planar with no lone pairs. There's nothing in there to give us any kind of a different structure or to move anything around. No lone pairs means that the molecular geometry is going to be the same as the electron structure. So once again, these two are the same. The next one, counting up the pairs of electrons around the central atom, they're all bonding pairs of electrons. There are no lone pairs, and there are 4 of them. So think about what that would be. Tetrahedral. And since there are no lone pairs, the molecular geometry, again, is going to be the same as the electron pair geometry, so it's tetrahedral once again. But now in the next one, we have our first instance of lone pairs appearing. In this case, we still have 4 pairs of electrons. So we're still, for the electron geometry, it's all about electron pairs. So this is still going to be a tetrahedral structure for its electron pair. But when it comes to what this looks like three-dimensionally, let's go to this next page now. I showed you an example here, down here, of tetrahedral. The first one, if you'll remember, our first one was was methane actually, CH4, and so it simply would have been the C in the middle and the H's out here in a tetrahedral shape. Now our next example, though, if you remember, was NH3, again tetrahedral shape, but for the electrons, but one of them is a lone pair. So we'll make that top one a lone pair. This is N, the rest of these are H's. Now if you look back a couple of pages back where I showed you all of the different types of structures, when you have a situation where you have tetrahedral for the electron pairs, but we have to imagine not being able to see this lone pair. If you look at all that's left, you'll see something that looks like a pyramid. And that is what it's called, is a pyramidal structure. So pyramidal for the structure. Some textbooks call it trigonal pyramidal, but I just call it pyramidal. The next one, H2O. Once again, we've got 4 pairs of electrons around. It's tetrahedral. It's going to have that tetrahedral shape, but this time there are 2 lone pairs of electrons. So look at this structure again. We've got the oxygen in the middle. We've got hydrogen, but this time some lone pairs. And we have to remember that these lone pairs, we have to imagine that we cannot see them. And if we can't see them, all that we have left is this structure, which looks kind of like a V shape, and we know that that's what the water molecule does. It has that Mickey Mouse head looking thing. Well, this is called a bent structure. So we've got a pure tetrahedral here. We have a pyramidal here when we have one lone pair. That's what it looks like, and it's so much easier if you will imagine these structures in your head. And over here we have the bent structure, sometimes called bent triatomic. I just refer to it as bent, but that is another name for it. So looking back here then, this is bent triatomic, or bent. Now, as far as polarity is concerned, if it is a pure structure, if there are no lone pairs around the central atom and all the peripheral atoms are the same, it's going to be nonpolar. We looked at that yesterday. So nonpolar for this one, if both the electron pair geometry and the molecular geometry are the same, it's going to be nonpolar. all of these first three are nonpolar. But as soon as we get down to a situation like these bottom two where we have lone pairs, those lone pairs are going to create uneven distributions of charge. And when they do, we're going to get a polar molecule out of that. So both of these are polar. So that takes care of our first three major structures: linear, trigonal planar, and tetrahedral, and the three different structures for tetrahedral depending on the number of lone pairs. Now let's go to the next set, and once again you're going to want to pause this and draw these first four structures, and then once you do that, then start it back up again, and I will scroll it down so you can draw the bottom one. So here are the first four, and there's the last three down here. So you need to pause it again and make sure you draw these structures. You've got to know what the Lewis dot structures are, or you're dead in the water as far as figuring out what the molecular geometries are. Okay, so back up here, let's look at PCl5. PCl5 has 1, 2, 3, 4, 5 pairs of electrons around the central atom. This is our Trigonal Bi-Pyramidal structure. If you look back at the table. And since there are no lone pairs, this Trigonal Bi-Pyramidal structure is the same molecular geometry. They're both Trigonal Bi-Pyramidal. We are going to again come back to the polar, non-polar discussion. The next example, SEF4, again has 1, 2, 3, 4, 5 pairs of electrons around it, so it's still Trigonal Bi-Pyramidal. But this time, we have a lone pair. So let's look at what this structure plays out. This first one is pure Trigonal Bi-Pyramidal. The next structure, however, we have the selenium. If you remember, the structure was SEF4. We have the selenium in the center. We have F here and F here. And in this particular case, when we have Trigonal Bi-Pyramidal, the lone pairs always form on the equatorial positions first. Remember, we said the equatorial positions were the ones here around that were circling around the center. You could kind of spin this like a top, and those ones that are spinning around the middle, those are your equatorial positions. So in order to show how this look a little bit better, I'm going to put the lone pair over here, and I'm going to put the other two fluorines on the robot arms, I guess. Remember that we have to pretend we can't see this particular lobe here where the lone pair is. Now this is the hardest structure for people to see usually. It was for me, because nobody ever told me that what I needed to do was make the little robot fall forward. If you make the little robot fall forward so that he's resting on his arms and let him rock back and forth, he's going to be a seesaw. It would be easier if you had some marshmallows and some toothpicks to look at and build these as we go to be able to see that. But again, if you let him fall over, rest on his arms, and teeter back and forth, he's going to be a seesaw. And that's the seesaw position. So that is exactly what they call it, is the seesaw position, or seesaw structure. The next one is another example of an electron structure that is Trigonal Bi-Pyramidal. There are 5 pairs of electrons around the central atom, so there's Trigonal Bi-Pyramidal. But now we've got 2 lone pairs. How does that play out? We are once again going to form it And I keep switching over before I remember what the structure is. It's BRI3, or actually I drew that wrong, didn't I? Okay, we're going to pretend that this originally said BRI3 instead of the other way around. Because when I drew the key for that, I drew it backwards, but it's going to work quite well this way as well. So let's go back here. BRI3, so we're going to put a BR in the center. We're going to put an I on top and an I on bottom. This time we're going to put the I out here just so you'll be able to see it better, and his arms are going to be the lone pairs. So lone pairs out here on his arms. Remember, we're not going to be able to see those, and all that's left over now is what we call the T shape. And maybe that's hard to see, but this time we're going to make him fall backwards on his tail. And if you fall backwards on his tail, you'll see that we have a nice little T shape. So this is a T-shaped molecule. Whoops. We can go back one. The next one, ICl2. I got that one right. ICl2, we're going to have I in the center and two Cl's around it. But if you notice, this one's kind of strange. We've got 1, 2, 3, 4, 5 pairs of electrons around the central atom. So it's still, yes, once again, trigonal bipyramidal. This is our last trigonal bipyramidal type structure. And now let's see how that plays out in our example over here. We've got I in the center, we've got Cl top and bottom, and this time all of our lobes out here in our equatorial position are lone pairs. And if that's true, then I've got all of these we have to imagine not being able to see, and all that's left over is this linear structure here. I think they should have called it something else besides linear, since that gives us no indication that there are lone pairs around that central atom, but that's what they call it. So looking back here then, it's going to be linear for this structure. The last three structures are all going to be based on an octahedral shape. So there's our 6 pairs of electrons around the central atom, octahedral. And since there are no lone pairs, it's still going to be octahedral for its molecular geometry. But now we go to the next one. The next one has, again, 6 pairs of electrons around the central atom. So it's going to be octahedral. But this time there's a lone pair. What does that look like? Let's go to our structures over here. We have the pure octahedral here. And it's kind of hard to imagine. There are only 6 lobes, and some people wonder why it's called octahedral. But if you drew these out and then attached all of these structures to each other, you would end up with this diamond shape that had 8 facets. So that's not a very great picture of a diamond there, but maybe you get the idea that if you attached all of those, you would end up with a diamond shape with 8 facets. So that's our pure octahedral. Now the next one, we had a lone pair. It doesn't really matter where you take it off on here, but I like to put the lone pair on the bottom, because if we do, I think it makes it easier to see that if we have this structure, and the structure that we're talking about this time is ClF5. So if we have the ClF5 structure, Cl in the middle, and F here, 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 and here, and we pretend that we can't see this one down here because it's a lone pair. Maybe it'll be a little easy for you to see that if we attach all of these lines, what we end up with is what we call a square pyramid. It is a square pyramidal structure. So if we have octahedral with one lone pair, it's square pyramidal. And finally, our last structure has 6 pairs of electrons around it again. Those 6 pairs of electrons make it an octahedral overall structure, or its electron pairs, but now it has 2 lone pairs. What's that going to look like? This time we have our structure. Again, I keep turning it before I remember what the formula is. XeF4. So I've got Xe in the middle. We're going to put a lone pair on top and bottom. It doesn't matter where the lone pair is, but they have to be straight across from each other. Lone pairs do not like each other. They're hugely repulsive. So top and bottom away from each other, and now the FEs come off around this central part. And if you imagine not being able to see this top and bottom section, maybe you can see that this xenon and the 4 fluorines would lay flat in your hand in a plane, in a square shape, and that's exactly what it's called, square planar. So that square planar shape is our final structure. So now that we know what all of our molecular geometries and structures are going to be, let's look at the polarity. As long as it's a pure structure, remember it's nonpolar. In this next one, it is not symmetrical, and since it's not symmetrical, it's going to be polar. It's got a lone pair around the central atom, and that's a big indicator, although there's a couple of exceptions to the rule. This next one, again, is not symmetrical. You can't draw any lines of symmetry, so this one's going to be polar as well. It's got an uneven distribution of charge. Now, next one is the example that I'm talking about. It does have lone pairs around the central element, but look at the symmetry. There's symmetry all the way around this one. This is one of our exceptions to the rule. Even though it's got lone pairs on the central atom, because of this symmetrical nature of its structure, and maybe you can see it better if you flip here to look at that symmetrical nature of its structure with that linear structure and the electron cloud all around the center of lone pairs. You can see that this is going to be a non-polar structure. It is an exception to the rule. SCl6 is pure octahedral. It's going to be non-polar automatically. ClF5, non-symmetrical. It's going to be polar. And finally, the last structure. The last structure does have lone pairs of electrons around it, but once again, it's very symmetrical in nature. You can draw lines of symmetry through it. It is a non-polar structure, our final exception to the rule.